Section 3.4 of the book deals with the treatment of sewage and wastewater chemistry. In the first section, the author talks about local treatment plants as direct dischargers into various water sources. So the schematic that he gives just talks a little bit about what you would see for these local treatment plants, which can include municipal waste, industries. Sometimes you have industries that are required to pre-treat their waste before they release them into the municipal stream, so they may go through a couple of rounds, or they may be a direct discharger into a water source after treatment if it meets certain levels. Okay, so the water that is released by a direct discharger must be of comparable quality to the body of water that it is being emitted into. So let me pull up my pen here. So whether it's a community, whether it's some sort of industry that you have, their wastewater is going into some sort of main control where it has to go through various processes to clean it up before it can be released into your water source, into a body of water. Now what he shows in the next section is the layout of a typical water treatment plant that relies on both mechanical and biological water treatment. So we're not looking at chemical water treatment here. We only need that for certain cases. But what you're going to do in the typical model is you're going to start out with a series of steps that are designed to remove larger parts of material. So large particulates such as wood, leaves, bits of plastic, anything that people get in the water stream get raked out. So all of that solid material is just raked out and taken out. The water will then go through a sand trap that will remove smaller particulates that didn't quite get filtered out by the rake. And then there is an oil and fat trap, which hopefully the oil and fat trap is redundant because most of the industries that are going to be releasing fats and oils are required to remove those in the first place. But it's a safety measure, it's a backup. Sometimes household waste is going to release oil and fat, so it's a good thing to still have in there. Now, those three processes alone will remove approximately 30 to 35% of the organic material from the water source. But, you know, that's part of it. You still have about 2/3 to go. So the rest of it is going to be in various forms. It might be dissolved in solution. It might be suspended within the body of the water, or it could be a colloid. So a colloid is just a very fine particulate matter that remains suspended in the solution. It's a little bit different particulate size from suspended particles that would eventually separate out. Colloids tend to remain suspended in solution without some sort of mechanism to remove those. Now for those materials, for that 2/3 that isn't removed by the first set of filters, you can rely pretty much on aerobic decomposition. So in aerobic decomposition, and I'm sorry I have a mouse right now, so I don't know if I can write with this or not. So aerobic decomp. Now in aerobic decomposition, you're relying on bacteria that use oxygen to start breaking things down. So what happens is that bacterial forms start breaking down that organic material, and you get what is known as biomass that forms. And this is in the form of what we call activated sludge right here. Okay, so this sludge is activated with these bacteria. There's a difference between activated and deactivated sludge. Okay. Now, the activated sludge can then be further broken down. That's not complete. Okay, so we've got air coming in here, we've got our biological treatment. Okay, so we've got this activated sludge. Now, it moves down here to the next phase of treatment. And notice we don't have any airflow coming in at this point. So this is where you get your anaerobic. Okay. Now, not every system will require both aerobic and anaerobic decomposition, but if it is required, this will further break down this biomass, and at this point you tend to get methane gas, which is CH4, and you get carbon dioxide gas, CO2. Okay, so that breaks it down through processes of fermentation and putrefaction. Anaerobic decomposition is actually used in several industries. Dairy, cheese making will rely on anaerobic decomposition. Beer, things that use yeast will also use anaerobic decomposition as part of their process. Okay, so we've got this anaerobic system down here. So here's your sludge putrefaction. So you've got your sludge moving through a variety of things. And notice that, so various things like right here, we've got phosphates that can be precipitated out. Phosphates may be present from what are known as tensids, which is related to detergents in the water. You want to remove all that, so eventually you can release that into the stream. You take your sludge down here, you break that down. You can collect your gases right here. Okay, you can dry this sludge, and now this is deactivated. Okay, I'm going to abbreviate that. So deactivated sludge can then be used as a fertilizer. It can be spread on fields. It has a high mineral content, it's good in nitrogen, it's good as a fertilizer at this point, and the biological activity has ceased in there, so it can be used as a deactivated fertilizer. Now in the next slide, he talks a little bit about the composition of sewage, different things that you're going to have in there. And this one's pretty self-explanatory. So when you look at wastewater, you either have undissolved components or dissolved components. Now the undissolved components are either going to be large enough to settle out, they're going to, you undergo sedimentation, sediment settles to the bottom, you filter them out, or you pour the water off the top. You can have swimming material that remains moving throughout the solution. It can either float to the top or be filtered out. And then you have suspended colloids. Now suspended colloids can be encouraged to clump together or group together. This is not using chemical treatment yet, but sometimes those colloids will sort of gather in and of themselves because of ionic charge, and so you can get little flakes of it appearing, you get flaking. All of these things can be filtered from the solution, just physical means of filtering. Now you also have components which are dissolved in the wastewater, and these are broken up into two categories. You've got your organic and your inorganic compounds. Now if it's organic, there are two subcategories. They're either degradable, in which case we can just use bacteria. So biological treatment, aerobic or anaerobic bacteria can degrade that organic matter and convert it into gases, and then we have a deactivated sludge afterward. Or the non-degradable. Now, non-degradable organics and inorganic compounds can be removed by a variety of means. So there's not one set means of doing that. Here are some various means that can be used. Physicochemical treatment, neutralization, precipitation, flocculation. If you remember from the water quality lab that we did measuring dissolved oxygen, we produced a flocculate. So we added a chemical that encouraged those colloidal particles to come together and make large flakes, known as a flocculate. And then that can be settled out of solution and separated out, or it can be adjusted in some other way. You're dealing with ions for these dissolved materials, so an ion exchanger can be used, thermal methods, electrochemical methods, adsorptive procedures. You can add something that these ions bind to the surface and then can be removed in that manner. So that's just a quick breakdown on the contents that you're looking at in your wastewater. Now this chart is just showing the variation in the amount of sewage coming from a municipal system per day, and this is an estimate for a moderately sized township of about 50,000 people. So this chart would change depending on the number of people, more or less. It's going to raise or lower. Now when it talks about municipal sewage, what is it talking about? Well, this is primarily going to be what you think of in sewage. It's going to be urine, it's going to be feces, and it's also going to be what is known as gray water. Water that's used for rinsing, showering, doing laundry, washing dishes, that kind of thing. All of that is coming together to make this domestic sewage. Now, if we look at this, the green line that we see right here is the daily, the daily average is the blue as they've averaged it out, but this is kind of how it's fluctuating over time. So this is the amount of matter that's settling out, cubic centimeters per liter that's settling out. So we're all the way from 0 to 1 all the way up to about 12 cubic centimeters per liter. And you can see that over the period of a day, so starting at midnight and going through, we have a low, and then as people begin to get up and go about their day, it starts coming up until it reaches a peak. And I'm sorry, I'm following the yellow line. I should be following the green line here. Okay, so we reach a peak and then it comes back down, and then what they've done is kind of normalized that and averaged it out in the blue. So there's a daily average, and then the pink that you see is the 24 average. Okay, so 24-hour average right here, and this is a little confusing. Okay, there we go. 24-hour average in the pink line, nightly average across the blue. Okay, so here's at night. The nightly average is down here, and then it raises up to a daily average, and then back down to the nightly average. Okay, and then the yellow line that you're seeing it's a little bit different. It's the matter that settles in the wastewater. So the particles that are large enough to settle out. And you can see that the curve is fairly different for the settling matter as opposed to the just regular material, the matter that's going to be in the sewage. So the amount that settles out kind of peaks a little bit earlier than the overall amount of material. But this daily peak, we're looking on the green line, here's kind of the daily peak, and you can see early afternoon, the amount of material coming through that sewage is going to peak. Now, why do we care about this? Well, this is very important to city planners. Anybody who's planning a municipal system needs to look at these averages to kind of determine what is the amount of water that you're going to have, and what's the amount of effluent, the amount of this sewage water that you're going to be taking on and dealing with. You want to adjust your system. You don't want to have it running at the same speed all the time, day and night. When your nightly average is down here, you don't need to be running quite as hard as you do as when it peaks up here in the daily average. So you've got to account for those peak times and for those lower times. You have to take all that into account when you're planning your system. Now, another thing that the author talks about, and this is one that I was hoping we would get to in lab, but we didn't quite have time to get to this because this requires measurements daily over several days, and that is the biochemical oxygen demand, BOD. Now, realize that anyone working in a water treatment plant is going to be doing this sort of measurement, a BOD, on a regular basis. And the biochemical oxygen demand is simply a measure of the amount of oxygen being used by aerobic bacteria during their oxidation process. So we know that aerobic bacteria use oxygen, and how much oxygen are they going to use? So you'll notice here that it starts, over the number of days, it starts out essentially at 0, and then it's rising over time, the milligrams of oxygen per liter. Now that's just the reason it continues to rise. It's not that the bacteria are using more and more oxygen, as the days go on. They don't increase the rate of consumption of oxygen, but the BOD is the measure from the initial point where they're not using any oxygen to whatever day it is. So it's a running total, basically, of the amount of oxygen they've used. And you'll see that it does initially tend to rise fairly rapidly, depending on your sample. Okay, so here's a sample that's readily degraded, something that the bacteria can easily break down. It rises very, very rapidly, and then it starts to sort of taper off, and then it picks up again. So these rapid rises are what you're seeing as the increase in the use of oxygen. But basically, when it reaches its maximum here is about 5 days. A readily degraded sample can be broken down in a matter of about 5 days. If you have other things going on in here, you have other materials in there, different types of substrates and whatnot, it can change that BOD profile. Or if you look at just the respiration of things that can easily be used by your substrate, by your bacteria there, then you can see kind of that overall check. So readily degraded sample, here's a sample you're checking it against, and then kind of the difference between those is what you're looking at. There are all sorts of calculations that go into calculating a BOD, and we may take a look at an example of how to calculate a BOD just so you're aware of that. We won't do it in this video, but we may look at that in the lab. Now in this section, the author looks at the anaerobic degradation of organic materials. So, as I said, sometimes industries, it may be a process for wastewater treatment where you have aerobic and anaerobic, although sometimes just aerobic is used. And there are some industries that require this anaerobic degradation. The manufacture of cheese, the manufacture of beer, both require anaerobic degradation. And also, some countries, some companies, not companies, but countries have kind of keyed into the idea of anaerobic degradation of these waste materials. The United Kingdom, Germany, and Denmark all use anaerobic degradation of waste material to produce fuel, and they recover the fuel because anaerobic degradation, as we said, will produce methane gas. And so about 60% by volume of the gas produced is methane, and then another 40% is other material, carbon dioxide, hydrogen sulfide, ammonia, hydrogen gas, things that, if they can be separated out, are actually useful gases. They can be applied commercially. So again, I'm not going to walk you through the total here, but you can see here's kind of your rate limiting step. The very first one, breaking down your carbohydrates, fats, and proteins, is very slow. And then you have a faster step for sugars, amino acids, fatty acids. This is where you kind of pump some energy over here and put it into this system. But these materials then can rapidly be broken down by bacteria that are acid-forming bacteria. And if you read in the book, he mentions the names of some of the bacteria that are used. There are actually specific strains of bacteria that can be applied, just like a winemaker or a beer maker will use specific strains of yeast. There are specific strains of bacteria that do the job here. And so the acid-forming bacteria will break it down into either methanogenic substances, sort of very simple hydrocarbon substances, so very short-chain acids and formate, acetate, methanol, small molecules, and then non-methanogenic substances that create these little bit larger molecules like propionate, butyrate, aldehydes, other alcohols. Now these small molecules can get broken down by methane bacteria, methane-producing bacteria. It's a fairly slow step, and then followed by a very rapid conversion by hydrogen and carbon dioxide. So about 70% of the material comes through this path, and you end up with this methane. Okay, over here, now you get acetogenic bacteria that then break it down into the methanogenic, and now we can put it through the same steps to get us to our methane. Okay. This slide just walks through just basic principles of the purification process for anaerobic degradation. And not going to walk you through all of these specifically. I think I had a link in here, and I'm not seeing my link, so I may have to come back and pick that up. We may pick that up at the very end here. But you can either have a one-step waste treatment plant or a two-step that can be applied in certain cases. If you have a rate limiting step up here, if this one tends to be slow, then you can put in the second one to speed it up. Otherwise, the one step is sufficient. This is a short clip talking about an actual anaerobic system that's being used on a dairy farm, but the practice would be the same for any anaerobic process.
Anaerobic digestion is a promising technology offering many benefits to society. Far too often, though, this method of organic waste treatment is touted only for its ability to produce renewable energy. However, anaerobic digestion also helps improve air and water quality, reduce greenhouse gas emissions, and can even be a source of job creation for local economies. Furthermore, the next generation of anaerobic digesters is at the center of a system of technologies capable of producing even greater benefits.
Digesters have been around for a while, but we've got new technology that allows us to take this to a better place economically and environmentally.
Traditional methods of dealing with the organic waste stream include sewage treatment plants, aerobic lagoons, compost yards, and landfills. However, unlike anaerobic digesters, these solutions more often than not consume rather than produce energy. Digesters come in many different designs. Some treat municipal sewage or urban food waste. Others process animal manure. In this video, we will use the example of a rural dairy-based system. But whatever their design, all digesters follow the same underlying concepts.
Anaerobic digesters are basically carbon conversion tools. They simply take the organic carbon that's inside the manure and turns it into a gaseous inorganic carbon, which is called biogas. Biogas is methane and carbon dioxide. It's the methane that we really want. We can use it for fuel or as power or electricity.
Without anaerobic digestion, manure management has traditionally been limited to simply storing untreated manure in lagoons and later applying the untreated liquid onto fields. However, this practice leads to potential air and water quality issues, such as nutrient overloading to soils, release of phosphates and nitrates to water supplies, and emissions of odorous volatiles, ammonia, and greenhouse gases, such as methane and nitrous oxide. Anaerobic digestion, as part of a system of integrated technologies, can address all of these issues.
It gives us the diversification to have more than one item to sell, and also helps us control the nutrients, the manure, and that sort of thing.
At the center of the system is the digester itself, basically a sealed tank where the organic material is broken down. On this dairy farm, cow manure and potentially off-farm organics from the community are collected in a holding pit, then pumped into the digester. The tank mimics the digestion process of an animal's stomach. Inside, the liquid is heated, agitated, and mixed in an air-free environment. This converts the solid carbon in the manure to biogas, which is collected, cooled, and used to power an electrical generator. The electricity can be sold to the local utility and sent out to the grid. The system itself creates the energy needed to keep the process going. Temperature and flow are maintained using excess biogas and heat reclaimed from the generator set. After the biogas is captured, the treated manure is pumped to a separator where the liquid is removed. The remaining solids can be used by the dairy as bedding for their animals or even sold for profit as a soil amendment or peat moss replacement. The treated liquid is stored in a lagoon for watering crops. Unlike untreated lagoon water, this liquid is significantly reduced in pathogens and virtually odor-free. For the current generation of anaerobic digesters, this is where the treatment process usually ends. However, even greater benefits and value can be gained by adding additional components to the system. One example is nutrient recovery.
Anaerobic digesters by themselves do not do a very good job of treating the nitrogen and phosphorus in the manures or organic waste. If you have too much fertilizer, too much nitrogen and phosphorus, it can be harmful for the soil and the plants. That's the case at some of our large animal farms. Therefore, we need nutrient recovery units to be associated with our digesters.
Nitrogen, in the form of ammonia, can be reclaimed using a revolutionary new technology developed by Washington State University and its industrial partners. The process is far less expensive than existing methods.
We can collect it and then make it into an ammonia sulfate fertilizer that farmers traditionally have used for years. An added benefit is that during this ammonia production process, we cause the phosphorus to settle out. So we get a 2-for-1. These concentrated biofertilizers can be used by the farmer and displace what they presently are doing in buying fossil fuel-based fertilizers. A combined digester and nutrient recovery system is a win-win because we make renewable energy, we solve a concern with nutrients, and we make revenue for the local community.
Another add-on technology relates to the scrubbing and compression of biogas. In this type of system, biogas is converted to renewable natural gas fuel instead of being used to generate electricity.
We're just in the middle of a tip from petroleum-based fuels to methane fuels, natural gas for trucking fleets and for cars. We have the technology now to produce renewable natural gas from the biogas that comes off the digester. It's clean to pipeline standards, is available for vehicle fuel for half the price of diesel.
While biogas scrubbing and nutrient recovery are already at commercial scale, pyrolysis and other related technologies are currently in development and hold great future promise.
In the future, we'll be able to take this the next step to clean, even drinkable water.
Construction of anaerobic digester systems helps state and local economies as well. In addition to tax revenue, it is estimated that in the state of Washington, for example, each digester project creates 15 to 20 full-time jobs during construction and 2 to 3 permanent positions for its operation. Despite their initial capital cost, with well-conceived business models, anaerobic digester systems offer significant economic savings and environmental benefit over the long term.
Everything kind of comes in, goes around, and goes back out as something usable.
There are synergies with this systems approach. We not only have the digester, but we've got these additional units that we can plug on, and that requires more capital, but also generates a lot more revenue, making a more profitable package and making this more replicable.
The advantages of anaerobic digestion are well documented. Waste management, renewable energy, biofertilizer production, greenhouse gas reduction, and more. With the incorporation of existing technologies and the development of future ones, the benefits will only continue to grow.
All right, so in the next section, talks a little bit about removing those suspended solids from the water. And so that's known as flocculation. So what are the kinetics of flocculation? How are you going to actually remove that material? Now this is a little bit of a different chart to look at. It's kind of a three-dimensional, if you will, plot. You've got 3 axes to keep track of here. You've got the colloidal efficiency here, so that's basically just a measure of how well this colloid suspends and comes together in solution. You have the rate gradient, how quickly they're coming together, and you have particle concentration that just tells you how much of that you have concentrated in solution. And the kinetics of it is going to vary depending on your source. So you can see, and if you look on the bottom here, this is supposed to help you kind of place these three-dimensionally within the cube. That's a reflection on the floor, so you can see where these two, you can kind of see where they fall on this axis and this axis. A little bit harder though, for these bottom two, so they reflect them downwards. So this part right here is the reflection of this one. This cube right here is reflecting right here. This one is reflecting down here, and this is where it's a little confusing. They've got this drawn as a dashed line. It looks like it is on the right side of that block, but it's actually behind it, and they're just trying to create that image where you can see it. It's a little bit below and behind this cube, and so you can see that relative to that reflection. So you can see that sludge and waste treatment actually, fall into this upper corner is actually fairly efficient. And then another way, if we look at this cutout right here through the waste treatment and the sludge, we can see the various steps of going through your filtration, your flocculation, and then putting it back into the groundwater, so you can kind of follow it back down that path. Now, you don't have to worry too much about this, but you just need to be aware that these methods that we apply are highly efficient compared to natural flocculation and removal of these colloidal materials. So we're actually doing a better job than natural systems than in pulling some of these things out. In this slide, we can see the effect of adding a coagulant to wastewater. This is from a commercial site, Ecologics Environmental Services, and this is one of many different materials that they sell commercially for the cleanup of wastewater. Now in this one, they are starting over here with raw wastewater from a food processing industry. And in the second one, they've added the coagulant. It is known as CLFCB. That's their trade name for it. You can see that it begins to create this precipitate. It begins to flocculate out. Here we can see that this flocculant negative polymer, this is the material they've added has a positive or cationic charge. So now we've got this polymer basically that forms and precipitates out of solution. They can separate it out, and then they have the treated or cleaned wastewater. And you can see here that their total suspended solids dropped from 750 parts per million down to less than 6. So very effective in doing an initial cleanup on that very cloudy wastewater. In section 3.4.9, the author looks a little bit about various chemicals that are used for coagulation, flocculation. Aluminum and iron are typically used. Here he's just showing the effectiveness of various materials with different ionic activities. So we've got aluminum with a 3+ charge, calcium with a 2+ charge, sodium with a 1+, and you can see here's the percent of residual clouding. So this is where it's completely cleaned up, no residual clouding. This is where it's completely cloudy, so you can see it starts up here at completely cloudy and then drops down to 0% cloudiness based on concentration of the materials down here on the x-axis. Now the reason we want to look at this is because it can be a little bit touchy. Aluminum tends to be more efficient. We can use a lower concentration of the chemical to achieve the same effect, but we have to be a little bit careful because this is like hydroxylated aluminum. So aluminum will form an aluminum hydroxide complex right here that actually can be taken out of solution and then put back into solution based on various concentrations and pHs. So it's a little bit of a touchy system. You have to catch it just at the right point. And then it looks at the precipitation of that aluminum hydroxide here. Here's surface potential. So when we look at the surface potential of these materials based on ionic charge, comparing them, the hydroxylated, it looks very different here than it does with this curve. Okay. So when you're looking at trying to precipitate various materials out of solution, if you're looking at metals as opposed to the organics that we've been looking at in previous sections, metals can be a little bit tricky depending on what the metal is. So first of all, what we need to realize is the pH range of the water during water treatment cannot vary greatly. So for example, we can precipitate iron 3+ out anywhere from a pH of about 3.5 all the way to 13 or 14. Well, we don't want our water to be at a pH of 3.5. We don't want it to be at a pH of 14. We want to keep it fairly moderate so that when we finish our treatment, it's ready to go back into our body of water. We want it to be about the same pH as the place we're putting it. And so the range of pHs that are permitted for water treatment during metal removal is about 6 to 9. So we've got to stay in this range right here. We want our pH to be somewhere in there. Now, for a lot of metals, you can see there's good overlap here. Okay, so we've got something that'll work. There are 3 things that tend to be used for precipitation. One thing is sodium hydroxide. Another is sodium carbonate, Na2CO3. And this is also known as soda. Okay, so that's what soda is. And then the other one is lime. Okay, we see this one here. Lime is calcium carbonate and or calcium hydroxide. Okay, so that's the lime right there. So if we look at the materials that we can use, and then we look at their precipitation ranges for the variety of metals. Okay, sodium hydroxide can be used to precipitate iron 3+ over a huge range, and including the range that we're looking at. So no problem there. Iron 3+ is not really precipitate dependent. Just like the sodium hydroxide there, we could also use soda or lime. They also work in that range. And it won't matter. Any of them will get it to crash out of there. But now let's look at, let's say, chromium. So we come here. Now, down at this range, not too much. We do have sodium hydroxide that we can use over this range. Okay. But now we've also got this lime here. Okay, so it expands the precipitation range when we add soda or lime to that sodium hydroxide. So it's actually calcium oxide here, or calcium hydroxide, that we're using that is going to work best to get us into that range. So the addition of lime actually helps us out with the precipitation of chromium. Okay, now if we look at cadmium, let's see, where are you? Right here. Okay, if we come over here, sodium hydroxide doesn't start kicking in until a pH of 10. Well, that's completely out of range for what we want. So what we're looking at for cadmium is actually going to be soda. That's the only one that works in the pH range that we allow. Okay, and now let me just qualify down here. It looks like if we look here, this helps us understand the chromium a little more. Iron, anything we use just crashes it out up in the range that we want. So yeah, by a pH of 4, which is lower than we want. So definitely by 6 to 9, the iron's out of there. Here's cadmium. We can see here's our sodium hydroxide and our calcium. Those aren't working for us. They don't kick in until a pH above 9. So soda's the only one that's down here in the range that we want. It's in that range. Okay, so those are no good. But now if we look over here at chromium, okay, we can see that soda does work to precipitate it out over this range of 6 to 9. Okay, we're going to kind of cut out above 9 there. But notice it doesn't really do a great job of precipitating it out. It never gets it down to 0. So soda, really not a good choice. Right, so if we look here at calcium oxide and sodium hydroxide, the calcium oxide, the blue line, goes to 0 and it stays there. Okay, that's what's important. Now sodium hydroxide comes down to 0 and then it kicks back up again. Well, if we're anywhere in this range, if we're up at a pH of 9, sodium hydroxide is going to allow some of that chromium to come out of solution. Calcium is going to keep it out of the solution. And it does it at about the same rate down here as sodium hydroxide. So calcium is going to be our best bet. Calcium oxide being sort of the product here for these two, for the lime. Okay, so it's kind of equivalent to those. In this slide, the author just talks about a sewage treatment plant that requires the precipitation of phosphate. Now, why is phosphate singled out from among the other polyatomic ions that may be present? Well, that's because phosphates can be added to a water system either from a direct source, they can be from a natural source, they can be from microbial byproducts, they may be from detergents. A lot of the older detergents contain phosphate. They're getting away from that a lot now, but there are a variety of industries that will use phosphate in manufacture, and so they have those in the water that have to be removed. Now the problem with phosphates is that they contribute to what's known as eutrophication. And there are different levels that you can have in lake systems. Eutrophication is when a lake or a body of water has become completely nutrient saturated. The water contains as many nutrients as it can hold, which sounds like it could be a good thing, but the problem is there are so many nutrients and so much food source for things like plankton and algae that you get these huge algae blooms, you get an overwhelming amount of plankton. There's more than the local fauna can handle and can remove from that system, and so you get these mats of algal blooms going on, and it chokes out a body of water. And so phosphates need to be removed from that system just so they don't over fertilize it, basically, put too many nutrients into the water. And There's a variety of ways to do that, but typically they're chemically precipitated with either aluminum or iron salts. And those can be used in various stages. So depending on the amount of phosphate you have and what you're doing, there are 3 places that you can precipitate out your phosphates, either during the sand trap phase, removing those smaller particulates, during your aerobic digestion, or if you're carrying out flocculation, you can do that there. So these are 3 points at which you can inject material for the removal of phosphates. The next several figures that the author presents in the book are what I like to call figures dealing with balancing acts. So they're just talking about other materials, other compounds that have to be kept in balance. I'm not going to go into those in detail. You can take a look at those in the book and look through these figures, but just be aware that there are several other things that require balancing out, such as the nitrates and ammonia with the oxygen demand of the materials that are in there, different organics, ways to eliminate phosphate from the system, so on and so forth. So do look through those. And in section 17 of this chapter, 4.17, he talks about how wastewater is treated from excess water from the metalworking industry, specifically from automobiles. And again, that's because the author is German, and so that is an important industry in Germany and in parts of the U.S. Not something that is as big here in our area. So again, I'm not going to go into detail of that, but if you have any interest in the auto industry and you want to know how their water treatment differs from, say, food industry that we have a lot of around here, or just municipal waste, take a look at this slide, read through the section in the book, and you can see where there's a few differences in there. And then in the last slide, he talks about combining all of these techniques. So what if you have a sewage treatment plant that combines mechanical, biological, and chemical sewage treatment? So putting it all in one block. He has a schematic here. Again, it's just all the parts that we've looked at put together, so you can kind of see how they flow together from beginning material to the end deactivated sludge, and then the water, the effluent that's put back into the original source. So you can see those, how they tie together. And then something else I would like for you to look at, in addition to this part of the book, is a little clip that was done by one of the local news agencies looking at one of the local water plants. So we'll take a look at that one next.
All right, 6:46 now. Have you ever wondered what happens to the water when you flush it down the toilet or pour it down the drain? Legends Brett Martin went to one state-of-the-art facility in the Ozarks. Good morning, Brett.
Hey, good morning, Shannon. City Utilities reports less than 5% of the water they treat is actually used for drinking. So what happens to the water that's wasted? Well, we found out exactly what it goes through before it's pumped right back into the water cycle. Raw water, septic tank discharge, or restaurant waste like fats, oils, and grease, or fog is treated carefully in Springfield.
If it's milk or some type of liquid or something that's been diluted, I would pour that down the drain. I have a garbage disposal, so it eats up pretty much anything I put down there anyway.
But after that, millions of gallons of wastewater flow into the Springfield Southwest Clean Water Plant, which treats 90% of the city's wastewater a day. Kelly Green is the plant manager.
We average about 28 million gallons a day right now.
He walked us through the 60-acre facility, which is manned 24 hours a day, 365 days a year. Water that goes through 4 stages and can spend 24 to 12 hours within the system.
This is our headworks facility. This is where the wastewater first comes into our treatment plant. We're going to screen out any of the rags, grit, grease. So as you can see, after the water comes out of our headworks, it flows in here. This is still the raw wastewater. From here it's going into our aeration basin, and this is where the treatment actually begins. So basically what we do is we create a specific set of conditions to cultivate a specific type of bacteria to consume the waste and to perform the treatment. Now we're in the clarification step. So what we do is we bring that water out of the aeration basin with all those microorganisms in it, bring it in here, and we slow the flow down. those bacteria and microorganisms settle to the bottom, and the clean water filters off the top. From the clarifiers, which we were just at, the next step, it goes through a small filtration step for any fine solids. Then it comes over to our ozone disinfection.
The plant uses ozone as a disinfectant before discharging and refueling Wilson's Creek south of the facility. North of the facility, the stream is usually dry, but when you get south of it, it becomes this beautiful stream, perfect for fish and other wildlife because that clean water facility uses ozone as opposed to chlorine.
It is the strongest oxidizer. The only residual is just oxygen.
Green says the people of Springfield and downstream should feel confident in the quality of water they're treating.
I really feel that people of Springfield should be proud of the wastewater plants that they have. Both plants are award-winning plants.
And Green says some of the waste taken out of the water, such as grease and oil, are broken down and turned into manure for some farmers in the Ozarks. The rest of it is reused and recycled.